Hello, grade 7s. Welcome to our next video on chapter 10, looking at patterns. We are going to be looking at section 10.4, so sort of going over questions based around that. Now, I really see this section as us looking at three different ways that patterns can be expressed. So we're going to be expressing them, and you already have been expressing them. Let me just make this a little bit thinner. As a table of values. So we've been taking our patterns and we've been showing them in a table of values. You have also already been expressing your pattern as an expression, so like 2x minus 3. And we'll be also looking at how we turn that into an equation, which we've sort of already been doing. We can show our patterns in an expression or an equation. And today, we're going to be adding how you can see graphs and represent graphs, see patterns and represent patterns in a graph. A graph is the third way. I gave it away by messing up. Okay, so there's these three different ways that we can show our patterns, and you need to be able to show and understand patterns in each of these forms. And whatever form you're given a pattern in, you actually can get whatever the other two that are missing. So we're going to go over how we can do all of that. So to start, we're going to talk about telephone poles. Now let's imagine that for every 1 mile stretch, so if these telephones were stretched over a mile, there needed to be these 3 telephone poles every mile. Now this makes a pattern. If this pattern were to continue, if there was going to be a second mile stretch, this is another 1 mile stretch, so now we're 2 miles total. How many telephones or poles are going to be needed in that section? Well, we're going to need 3, but we actually already have this one which shares with both miles. So how many more telephone poles will we need to add to have 2 miles of telephone poles? Well, we would need to add another telephone pole here. Let's make it small. And then another telephone pole at the end. And so we needed 3 telephone poles for 1 mile. 1, 2, 3. But for 2 miles, when we add that second mile, we don't need to add another 3 telephone poles. We just add another 2 telephone poles. Now, if we were going to continue this pattern, we would just be adding another 2 telephone poles for every mile. And so every mile, you add 2 telephone poles. Now, we can turn this pattern that we see with how many telephone poles you have for miles into a table of values. So let's do that. On our table of values, I would have number of miles first, because that is the independent value. It is just the number of miles determines how many telephone poles you need. So number of telephone poles is the other number that we're looking at. So number of poles. So we already saw that in the first mile, if you just have a 1 mile stretch, you need 3 telephone poles. If you're going to have a 2 mile stretch, for there to be 3 telephone poles every 2 miles, you're going to need to add 2 more telephone poles because the 1 telephone pole shares on both miles. So you'll add 2, and you're going to need 5 telephone poles total. If you were to stretch your line for 3 miles, you're going to need 7 telephone poles. And this pattern can continue. We see that it's going up by 2 each time for every mile. 1 mile it goes up. So for 4 telephone poles, we would get to 9. For 4 miles, we would need 9 telephone poles. Okay, so now that we have our table of values, we can use this. I find the easiest way to find our expression. So the second way of showing our expression, the second way of showing our pattern, I find it easiest to find that expression from my table of values. So again, the things that I'm looking at, I am going to be looking at how much my value goes up by. So it's going up by 2 every time. and that's going to tell me what my numerical coefficient is. These are linear patterns, so they always go up by the same amount every time. That's how you know if it's a linear pattern, is it going up by the same amount every time. And this one is. It's annoying though, this keeps getting so, the line keeps getting so thick. So that tells me how much I'm going to be multiplying by. So let's say we had n number of miles. We had this variable. We didn't know how many miles we were going to have to build for. But we wanted an expression that tells us how many poles we need built in that many miles. Well, since I see that it's going up by 2, that tells me the multiplier. So I know that I'm going to be taking my number of miles, and I'm going to have to times it by 2. So if I take 1 and I times it by 2, I get 2, which is, I'd have to add 1 to get to 3. Well, let's see what happened if I had 2 miles. 2 miles times by 2, because there's 2 telephone poles being added for every mile. 2 times 2 is 4, plus 1 is 5. 3 times 2 is 6, plus 1 is 7. 4 times 2 is 8, plus 1 is 9. So I can see that the number of poles I need is 2 times by the number of miles, and maybe actually we'll make this variable m. So 2 times m, the number of miles, plus 1. And this makes sense when we look at our pattern. Okay, we had 3 telephone poles at the first one. For every telephone pole, we needed to add, or sorry, for every mile, we needed to add 2 telephone poles each time. So if we added 10 more miles, we would need 2 telephone poles each time. 2 times 10 would be 20. But at the very start, we had this one extra telephone pole that is not sharing with another one. And so it's always going to be 2 telephone poles being added every mile, plus that one initial one from the very beginning. Okay? And we could go back. If we wanted to find out another way to find that constant, we could go back to, well, what if we had 0 miles? Well, if this was going to go backwards to something added 2 to get to 3, there would have to be 1 telephone pole at the beginning at 0 miles. So when we go backwards to 0, we find that number. That gives us our constant here. So this would be our expression. Okay? That shows, in terms of miles, how many telephone poles we need here. And we can use our table of values to find that. Okay, so we have my table of values here, which I've sort of made a bit of a mess of. We have our expression. Now we can also show this pattern as a graph. And so we can, let's see if I can just move this over a little bit. We can actually graph these now, because each one of these has made an ordered pair. So 1 and this 3, they go together. When there's 1 mile, we always need 3 poles. When there's 2 miles, we need 5 poles. When there's 3 miles, we need 7. And so these make some ordered pairs, these numbers that go together. So we can actually graph these. Now, one good question is, well, how do you know which one's y and which one's x? So x is usually the independent variable. We've talked about this. So that's the one that doesn't, or that isn't changed by the other value. And so it's sometimes sort of hard to figure that out in certain situations. But when I think here to my telephone poles, so if I have, if I have 5 telephone poles, well, that tells me how long that would be stretched over. But it's how long of an area that I need that's going to determine how many telephone poles I need. So the miles, if this makes sense, they're not changed. It's the number of poles that you need per miles that changes. So that is dependent on the other one. So the dependent variable is always y. So x always goes first. I'm actually just going to clean this up here, I think. Sorry. So x always goes first. Whoa. And then it's y. Now, these are x and y, so we actually have these coordinates. So if I was to make a Cartesian plane. I'm not going to have it quite centered here, but I will have a bit of each quadrant. So if it was to look like this, I had 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. We can actually graph this. We said when I had gone 1 mile, and this, my x would show how many miles we've gone. My y I should label as poles. When we went 1 mile, we said we needed 3 telephone poles. When we went 2 miles, we said we needed 5 telephone poles. When we went 3 miles, that continued up to 7 telephone poles. And that graph could continue. It would, I mean, you know, you're not going to be able to, my graphing area is too small, but this can also continue backwards as well. We said when we were at 0, there was 1 telephone pole needed, and actually it doesn't really make sense, but this could continue backwards. And you'll notice that this graph makes a straight line that connects all of these. So every time, every step, for every 1 move over, so for every 1 move to the left, every 1 increase in miles, we increase the number of poles by 2. So it was 1 to the right and 2 up would be a way to describe this graph. But that's because you need 2 poles for every mile added. Okay, and so we can demonstrate this pattern as a graph as well. And since it's a straight line, that tells us that this is a linear relation. That's what we're looking at. These relationships that make graphs that go in a straight line that continue to increase or decrease at a constant rate every time. That's going to make a graph in a straight line. Okay, so we have this x and y. I just want to quickly talk about this. Y here, x we said was we had the variable of m. And y we said was 2m plus 1. Let me just spin this out. So I'm just going to emphasize this. Y we said was 2m plus 1. So in this case, our equation, we could say, is y is equal to, well, y we said was equal to this expression. So y is equal to 2, and we said m is equal to x, 2x plus 1. Okay, the x value of our graph times by 2 plus 1 is going to give us our y value. And we can look at our graph. We look at 1 here on the x coordinate. 1 times by 2 is 2, plus 1 is 3, and that's where we end up on the y-axis. 2 times 2 is 4, plus 1 is 5. That's where we end up on the y-axis. Okay, and so this is our equation. When we're looking, instead of just an expression, but an equation, we can make an equation in terms of y and x, right? The x coordinates on our graph and the y coordinates on our graph. We can make this equation of what y is equal to in terms of x. And so this is another way that we can look at patterns. So let's go look at a few more examples. So let's say we had this table of values to start with. Now we can use this table of values, which is one way of demonstrating a pattern, and we can change it into an expression, an equation, as well as turn it into a graph. And so we're going to do each of those things quickly now. So we have our x and our y value. So let's actually turn it into a graph right away, because this one already shows x and y. So our x values and our y values together, they make some coordinate pairs. So pairs that go together on our graph. So let's quickly make another Cartesian plane. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. Okay, and when x is equal to 1, y is equal to 0. So x is 1, y is 0. That dot would end up being right here. When x is equal to 2, y is equal to 2. So x is 2 and y is 2. That coordinate is right there on our Cartesian plane. When x is 3, y is equal to 4. So x is 3, y is 4. That would go right here. And x is 4 and y is 6. That would go right here. Again, this makes a straight line going across our graph, so it's a linear relationship. And it could continue either way. We could imagine this graph continuing this way. It would come off the page. It could also continue this way in that straight line. And we see that when x is equal to 0, and if x is 0, then y is equal to negative 1. That's negative 2. So y is equal to negative 2. Okay, so this is our graph. We can take our table of values to make this graph. We can also take this table of values and we can make an equation and an expression. So let's just erase these. We have a bit less to see. So how to do that? So y is equal to something. What do we have to do to x to make it equal to y? So x is going up by 1 each time. 1, 1, 1. Well, how much does y go up by each time? Y is going up by 2. So that tells us what our multiplier is, what our numerical coefficient is. So we're going to have to times x by 2 to get it to equal y. So y is going to be equal to 2 times by x. So does that work? 2 times 1 is 2. That's not 0. So there's something messed up here. If we had to figure out what it was, 2 times 1 is 2. Minus 2 would be 0. 2 times 2 is 4. Minus 2 is equal to 2. So it's 2x. And then if we look back, we can always look at what our x is equal to when it's 0 to find what our constant is. 2x minus 2. Y is equal to 2x minus 2. So if I take x in each time, so x is equal to 4, I can substitute that in for x. Does that tell me what the y is equal to? Does y equal 6 then? Well, 2 times 4 is 8, minus 2 is equal to 6. So that works for that situation. And so here's an equation that we have that also shows the same pattern. So we have this pattern in the table of values. Table of values. We have this pattern in an equation. And we have this pattern in a graph. Okay? 3 different ways. Let's now look at this one. Okay, so this case, we are given an equation. Okay? How can we take that equation and turn it into a graph and turn it into a table of values? So the easiest way to do this is to first make a table of values. So we're going to make a table of values of x and y. Now we could start at x is equal to 0. So if x is equal to 0, we substitute 0 in for x. So what if x, instead of just being x, is 0? That would mean it would be 2 times by 0 minus 3. Well, 2 times 0 is 0, minus 3 is negative 3. So y would be equal to, if this was 2 times 0 minus 3, y would be equal to negative 3, because 2 times 0 is 0. Well, what if x is equal to 1? We substitute 1 in for x. 2 times 1 is 2, minus 3 is negative 1. What if x is equal to 2? Substitute 2 in for x. 2 times 2 is 4, minus 3 is 1. Substitute 3 in for x. We're making our table of values. 2 times 3 is 6, minus 3 is 3. 4 in. 2 times 4, substituted in for x here. 2 times 4 is 8, minus 3 is 5. Okay, and we have our table of values, and this can continue for quite a while. Again, we can see that it is going up. The pattern is going up by 2 every time. 2 by 2 by 2. The linear pattern is consistent, going up by the same thing. That 2 is telling us what our numerical coefficient is, how much it goes up by each time. And when x is equal to 0, that what y is equal to tells us what our constant is. Okay? Anyways, once we have our table of values, we're able to graph this because together they make some coordinate pairs. So each one of these, this x and y value together, they make coordinate pairs. So when x is equal to 0, y is equal to -3. So if x is 0, y is -3, that would be down here. Why don't I quickly label this? 1, 2, 3, 4, 5, 6 on the x. This would be 0 and 0. And then -1, -2, -3, and 1, 2, 3, 4, 5, 6. Okay. So we said when x is 0, y is equal to -3. When x is equal to 1, if we go to 1 on the x-axis, the horizontal axis, y is equal to -1. When x is equal to 2, it says y is equal to 1. When x is equal to 3, when x is 3, we see that y is equal to 3. So we find 3 on the x-axis, we go up to y is equal to 3. When x is equal to 4, y is equal to 5. And we have this graph that shows a straight line. That wasn't a very straight line, but shows this linear pattern on the graph. Okay, so we have our y values and our x values that we can show on there. So 3 different ways of showing this pattern, y is equal to 2x minus 3. All right, okay, and the last one, what if we were given a graph? Could we find an equation, and could we make a table of values from this? So yes, we can definitely do that. The easiest way to go from graph and table of values, or to do graph to table of values graph is very quite simple. So we can look at this and we can make a table of values knowing x is our age. Okay, so we have our x value, which is age. And we have our y value, and the y value is allowance. Whoa. So this is talking about how kids, or one specific kid at least, at different ages, is getting a different amount of allowance, a different amount of money from his or her parents each week. So the allowance in dollars. So these are our x and our y values. And so we can see there's only some points plotted on here. But when the child was 4, the dots right here, that means that they received $2. Okay, so at age 4, they got $2. Next we see at age 5, it's not shown here, but age 5, they received $3. At age 6, they received $4. At age 7, they received $5. Now you could imagine that this pattern could continue. So what would the allowance be when that child was, I don't know, 16 years old? Okay, the child gets to be 16 years old. What is the allowance? Well, we can look at this pattern, and we can make an expression that we could use to calculate that. So the allowance is actually going up by 1 each time. So that's actually our numerical coefficient is actually just 1, which we don't ever really need to show. So our y is going to be equal to, what do we need to do to x to make it equal to y? So it's equal to x, and then, but it's not just equal to x, but we have to subtract 2 from x to get what the allowance is. You probably have seen that. The allowance is always 2 less than the age. So the age is 4 minus 2 is 2. When they're 5, you subtract 2 from that and you get 3. When they're 6, you subtract 2 from that, you get 4. So x minus 2 is the expression that shows the allowance. And so we have this equation that y is the same as x minus 2, or y is equal to x minus 2. And so if the student or the child is 16 years old, how much will their allowance be? If y is allowance, 16 minus 2, so y would be 14. Their allowance when they're 16 years old, if that's their x value, which is age, their allowance would be $14. Y, the dollars, y would be equal to 14. And so we have this, we can show these relationships, these patterns between two things, in this case age and allowance, with an equation. You can show it with a table of values, and you can show it with a graph. And in the questions that you're doing, you're going to have to be able to sort of switch between or find each of these, with whatever one you're given. So sometimes you'll be given a table of values, you'll need to find an equation that goes with it. Sometimes you'll be given a graph, you'll need to make a table of values from that. You'll be given an equation, you may need to make a graph from that. And that's how we're looking at just these three different ways of representing these linear patterns, these patterns that increase or decrease at a consistent rate. Okay, so there'll be an assignment that will be going up with this video, so check the Google Classroom, and I will be available Thursday to help with any of those questions. Of course, there's always other YouTube videos and stuff you can check. Make sure you look through the examples in the textbook is a good place to look at, get some examples of how to do some of those questions that you will be assigned. Okay, have a good day, grade 7s. I will talk to you later.